According to the National Electrical Code, specifically Article 300.3, C, conductors of different systems, circuits, and voltages are permitted to occupy the same equipment wiring enclosure, cable, or raceway. The code stipulates that unless otherwise permitted, these conductors must be separated by a barrier. In the situation of installing low-voltage equipment and using a chase conduit upwards to route plenum-rated cabling, the practice of placing a polytube within the conduit to accommodate a sensing line into the controller is generally permissible, contingent on adhering to specific conditions within the NEC. This hinges primarily on two factors: firstly, not overfilling the conduit, and secondly, the polytube effectively acting as a barrier to separate the low-voltage cabling from the sensing line. Article 300.3 C of the National Electrical Code directly addresses the scenario where different electrical systems share the same enclosure or raceway. This article is crucial because it acknowledges the reality that in many electrical installations, space is a premium, and running separate conduits for every system isn't always practical or feasible. However, the code also recognizes the potential hazards associated with mixing different electrical systems within the same enclosure, such as interference, voltage induction, or even physical damage due to incompatible wiring methods. The key provision of Article 300.3 C is the requirement for a barrier between different systems. This barrier doesn't necessarily have to be a physical, rigid divider. In many cases, it can be achieved through the use of proper insulation grounding techniques, or, as in the case you described, a non-conductive conduit or tubing. The polytube, in this context, serves as that barrier, ensuring that the low-voltage cabling is electrically isolated from the sensing line. Several factors influence the suitability of using a polytube as a barrier. Firstly, the material of the polytube must be non-conductive and compatible with the environmental conditions within the conduit. It should be resistant to moisture, temperature fluctuations, and any chemicals that might be present. Secondly, the polytube must be properly installed to ensure that it provides continuous separation between the different systems. This means that it should extend the entire length of the conduit and be securely fastened at both ends to prevent it from shifting or dislodging. Thirdly, it's important to select a polytube that is appropriately sized for the application. It should be large enough to accommodate the sensing line without overcrowding the conduit, but not so large that it takes up excessive space and makes it difficult to pull the low-voltage cabling. Overfilling a conduit can lead to several problems, including difficulty in pulling wires, damage to insulation, and reduced heat dissipation. The NEC specifies maximum fill percentages for conduits, which must be adhered to ensure safe and reliable operation. These fill percentages vary depending on the type and size of the conductors, as well as the type of conduit. In the context of your question, it's crucial to calculate the total cross-sectional area of all the conductors and cables within the conduit, including the sensing line and the polytube. This total area must not exceed the maximum fill percentage specified in the NEC for the particular type and size of conduit being used. The NEC provides detailed tables and formulas for calculating conduit fill, and it's important to consult these resources to ensure compliance. If the conduit is overfilled, it may be necessary to use a larger conduit size or to reduce the number of conductors or cables within the conduit. Failure to comply with conduit fill requirements can result in code violations and potentially hazardous conditions. When installing electrical systems, it's always important to consult the latest edition of the National Electrical Code and to follow all applicable local codes and regulations. The NEC is a comprehensive set of standards that covers a wide range of electrical installations, and it's essential to have a thorough understanding of its requirements to ensure safe and compliant installations. In addition to the NEC, local codes and regulations may impose additional requirements or restrictions on electrical installations. These local codes may be more stringent than the NEC in some areas, so it's important to be aware of them and to comply with them accordingly. In summary, placing a polytube within a conduit to separate low-voltage cabling from a sensing line is generally permissible under the NEC, provided that the polytube acts as an effective barrier and that the conduit is not overfilled. It's important to consult Article 300.3 C of the NEC and to follow all applicable local codes and regulations to ensure a safe and compliant installation. Always prioritize safety and compliance when working with electrical systems. Remember to properly ground all equipment and to use appropriate personal protective equipment. If you are unsure about any aspect of an electrical installation, it's always best to consult a qualified electrician. The electrical code is very specific and provides guidance on a wide variety of electrical installations. Several other articles may be relevant to a low-voltage installation of this type. Article 725 covers Class 1, Class 2, and Class 3 remote control, signaling, and power-limited circuits. This article will be important if the low-voltage equipment falls under one of these classifications. It specifies wiring methods, overcurrent protection, and other requirements specific to these types of circuits. Article 725.55 addresses physical protection and specifies where and how Class 2 and Class 3 cables must be protected from physical damage. Article 725.136 covers wiring methods and specifies the types of wiring methods that are permitted for Class 2 and Class 3 circuits. Article 800 covers communications circuits. If the sensing line is part of a communications circuit, then this article would apply. It covers wiring methods, grounding, and other requirements specific to communications circuits. Article 800.110 covers access to electrical equipment behind panels designed to allow access. Article 800.133 covers the types of cables for communications circuits. Chapter 9 contains tables and examples that are helpful for calculating conduit fill, ampacity, and other electrical parameters. These tables and examples are essential for ensuring compliance with the NEC. Annex C provides examples of conduit and tubing fill calculations. These examples can be helpful for understanding how to calculate conduit fill in various situations. Firstly, ensure all components are rated appropriately for the installation environment, including temperature and moisture. Secondly, verify that the conduit is properly supported and secured. Thirdly, label all conductors and cables clearly to identify their purpose and voltage. Fourthly, use appropriate connectors and fittings for the type of conduit and conductors being used. Fifthly, perform a thorough inspection of the installation before energizing the circuit. Sixthly, document the installation and keep records of all materials used and tests performed. Several different types of conduit can be used for electrical installations, including rigid metal conduit, intermediate metal conduit, electrical metallic tubing, flexible metal conduit, and rigid polyvinyl chloride conduit. Each type of conduit has its own advantages and disadvantages, and the choice of conduit will depend on the specific application. Rigid metal conduit, or RMC, is a heavy-duty conduit that provides excellent protection for conductors. It is typically used in areas where there is a risk of physical damage or corrosion. Intermediate metal conduit, or IMC, is a lighter-weight version of RMC. It provides good protection for conductors and is easier to work with than RMC. Electrical metallic tubing, or IMT, is a thin-walled conduit that is commonly used for indoor applications. It is lightweight and easy to install. Flexible metal conduit, or FMC, is a flexible conduit that can be used in tight spaces or where there is a need for movement. It provides limited protection for conductors. Rigid polyvinyl chloride conduit, or PVC, is a non-metallic conduit that is resistant to corrosion. It is typically used in underground or wet locations. The NEC provides detailed requirements for the installation of each type of conduit, including the type of fittings that must be used, the spacing of supports, and the methods for grounding the conduit. In general, metal conduits must be grounded to provide a path for fault current and to protect against electric shock. Grounding can be achieved by bonding the conduit to a grounding electrode conductor or by using listed grounding fittings. Non-metallic conduits do not need to be grounded, but they must be installed in accordance with the manufacturer's instructions. It is important to select the appropriate type of conduit for the application and to install it in accordance with the NEC and the manufacturer's instructions. A properly installed conduit can lead to electrical hazards and code violations. Consider voltage drop, especially in long runs. Calculate the voltage drop to ensure it remains within acceptable limits as specified by the NEC. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Properly size conductors based on the load and length of the run to minimize voltage drop. The NEC provides tables and formulas for calculating voltage drop. It's important to understand the difference between Class 1, Class 2, and Class 3 circuits as defined in Article 725. Class 1 circuits are power-limited circuits that operate at up to 30 volts alternating current or 60 volts direct current. They are typically used for remote control and signaling applications. Class 2 circuits are power-limited circuits that operate at up to 30 volts alternating current or 60 volts direct current and have a maximum power output of 100 volt amps. They are typically used for low-power applications such as doorbells and thermostats. Class 3 circuits are power-limited circuits that operate at up to 30 volts alternating current or 60 volts direct current and have a maximum power output of 0.5 volt amps. They are typically used for very low-power applications such as smoke detectors. The NEC specifies different wiring methods and overcurrent protection requirements for each class of circuit. It's important to identify the class of circuit correctly to ensure that the installation complies with the NEC. Consider the environmental conditions in which the equipment will be operating. The equipment and wiring must be rated for the environmental conditions, including temperature, humidity, and exposure to chemicals or corrosive substances. If the equipment will be operating in a wet or damp location, then it must be rated for wet locations. If the equipment will be operating in a hazardous location, then it must be rated for hazardous locations. The NEC provides detailed requirements for equipment and wiring in various environmental conditions. If running low voltage and line voltage in the same conduit, ensure proper insulation and separation. Follow NEC guidelines for separating different voltage systems within the same raceway. Consider using barriers or dividers within the conduit to maintain separation. Check local amendments to the NEC, as some jurisdictions may have additional requirements or restrictions. Always consult with local authorities to ensure compliance with all applicable codes and regulations. Stay updated with the latest edition of the NEC, as it is revised every 3 years. Changes and updates to the NEC can impact installation practices and requirements. Consider future expansion needs when designing the electrical system. Provide adequate capacity and space for future growth and changes. Plan for additional conduit runs or larger conduit sizes to accommodate future wiring needs. When pulling conductors through conduit, use proper pulling techniques and lubrication to avoid damaging the insulation. Use listed pulling compounds or lubricants that are compatible with the conductor insulation. Avoid excessive pulling force, which can damage the conductors. When terminating conductors, ensure proper connections and torque. Use listed connectors and terminals that are appropriate for the conductor size and type. Tighten connections to the manufacturer's specified torque to ensure secure and reliable connection. Always disconnect power before working on electrical equipment. Use appropriate lockout/tagout procedures to prevent accidental energization of the circuit. Verify that the circuit is de-energized using a voltage tester before beginning work. Regularly inspect electrical systems for any signs of damage or deterioration. Check for loose connections, damaged insulation, and corrosion. Address any issues promptly to prevent electrical hazards and equipment failure. Maintain accurate records of all electrical installations, including wiring diagrams, equipment specifications, and inspection reports. These records can be helpful for troubleshooting and maintenance purposes. Follow manufacturer's instructions for all equipment and materials used in the electrical installation. The manufacturer's instructions provide important information about the proper installation, operation, and maintenance of the equipment. Consider energy efficiency when designing the electrical system. Use energy-efficient lighting, motors, and other equipment to reduce energy consumption and costs. Implement control systems to optimize energy usage. Properly size electrical panels and distribution equipment to accommodate the load. Ensure that the panel has adequate capacity for all circuits and equipment. Avoid overloading panels, which can lead to overheating and electrical hazards. Protect electrical equipment from surges and transients. Use surge protective devices to protect sensitive electronic equipment from damage caused by voltage spikes. Properly ground all surge protective devices. Ensure that all electrical work is performed by qualified and licensed electricians. Electrical work can be dangerous and should only be performed by individuals who have the necessary training and experience. Follow all safety precautions and use appropriate personal protective equipment. Ensure that all electrical installations comply with the Americans with Disabilities Act accessibility guidelines. Provide accessible outlets, switches, and other electrical components. Follow the ADA guidelines for reach ranges and mounting heights. Consider the impact of electromagnetic interference on sensitive electronic equipment. Use shielded cables and filters to minimize interference. Separate sensitive equipment from sources of electromagnetic interference. Regularly test ground-fault circuit interrupters to ensure proper operation. GFCIs are designed to protect against electric shock and should be tested monthly. Replace any GFCIs that fail to operate properly. Properly dispose of electrical waste, including used batteries, lamps, and electronic equipment. Follow local regulations for the disposal of hazardous waste. Recycle electrical materials whenever possible. Be aware of the potential hazards associated with arc flash. Arc flash is a dangerous electrical phenomenon that can cause serious burns and injuries. Use appropriate personal protective equipment and follow safe work practices to minimize the risk of arc flash. Conduct an arc flash hazard analysis to determine the potential risks and to implement appropriate safety measures. Article 110.16 requires that electrical equipment be marked to warn qualified persons of potential arc flash hazards. Article 110.24 requires that employers provide employees with training on arc flash hazards and safe work practices. Consider the use of renewable energy sources, such as solar panels and wind turbines. Renewable energy sources can reduce reliance on fossil fuels and lower energy costs. Ensure that renewable energy systems are installed by qualified professionals and comply with all applicable codes and regulations. Follow best practices for electrical safety to prevent accidents and injuries. Continuously improve electrical safety practices through training, education, and awareness programs. Promote a culture of safety in the workplace. Remember that electrical safety is everyone's responsibility.